Thank you. Very interesting question, and for those interested, I can provide the references to the works of Dr. Manley from USA, who published a couple of papers exactly not related in any extent to LNRR, but exactly to tracking the science of breezers in solid-state physics. And there are, for instance, it's very abnormal thermal expansion behavior. In some cases, instead of expansion, we have reduction due to asymmetry of breezer oscillations and such and such and such. But I can tell you why these breezers are so elusive, because actually my estimations show that, for instance, under conditions of LNR at electrolysis, the concentration, the mean concentration of breezers is just 10 to 3 or 4. Means per atom it's 10 to minus 20. So it's a hard, it's not easy to see there unless the activity results in such a dramatic event like energy production. Then they become visible.
Yeah. One thing I want to say, I have one question and one comment. You said that beam experiment destroyed everything, but why we are measuring such things is just to show the electron screening effect. So I don't know lattice structure, that's okay for us because there's electrons there. That's one point.
Yeah, it's a very good point, because being a freshman, I've already done several presentations, and both in my country and abroad. And I heard from the so-called, normal nuclear community, the first question: wow, what does solid state have to do with our nuclear physics? And my answer was, look at the experiments of this guy with your beams showing you that indeed there is an influence. So I think that these experiments are very relevant in principle, but another point is that of course they don't imitate the conditions of a real LNR. It doesn't mean that we don't need them. We need them, of course.
My question is, so if your model is real, then you can fuse the DED.
Yes.
But then the problem is the decay process. How do you think about it?
Sorry, then what?
Decay of the helium intermediate state without any emission of particle or neutrons.
Well, if you allow me to show the slides again, is it possible to show the slides again? Somehow. No? Okay. Here. Oops. Oh, maybe it will be too long. Okay, I'll try to answer. Of course, as I told you, this model doesn't require new fundamental physics. But understanding of the results of reaction, of course, probably requires some new thinking. But the state-of-art answer is I would be surprised that completely different conditions of LNR would result with the same reaction products. So that's the general statement.
Question?
Fabrice David. In another life, I was a molecular biologist, and it is well known that in the field of molecular biology, discrete briefer, play a very important role. Before asking my question, I want to bring element of response, element of answer, excuse me, to Dr. Negro. In a seminal work, Professor Doxois of École Normale Supérieure in France shows that discrete briefer actually exists in DNA. And there is also strong proof, strong evidence of discrete briefer in some quasi-crystal by neutron diffraction. Dr. Codens at the French Atomic Energy Department Commission shows that copper atom in some quasi-crystal will be some 100 over the mean temperature of the crystal. My question is if there is hotter part in crystal, like discrete briefer in palladium, if there is hotter part, if we want to follow the rule of thermodynamics, did you agree that there is probably the existence of cooler part in other part of the crystal? And if there is cooler part with temperature, local temperature, well under the mean temperature of the crystal, it will be very important, for example, to allow the existence of quantum condensate.
Thank you very much for your question, because it will allow me to show you the rest of my slides. First, this is a protein nanocluster. Actually, from your field of science, it's been investigated by my colleague, Professor Francesco Piazza from Orléans University. And he understood probably more than 5 years ago already, he understood that there is a striking site selectiveness of breather formation in protein structures. And when he looked closer, he understood why. Because breathers in this structure, as compared to regular structure crystals, they always arise at the same places. And in these places are characterized by increased conductivity and decreased clustering coefficient, so to say. Which means that indeed the disorder is produced during the electrolysis, and here the Strauss says the cracks and small particles are the yin and yang of the cold fusion environment. And now looking at these molecules, big clusters, we start to understand why. Then your link to the quasi-crystals is also very relevant, because during this conference, Billy Erie brought my attention to this picture. This is a new picture demonstrating this excellent experiment producing heat energy in 10 out of 10 runs. In the experiment, this energy of the scale of kilowatt, and the peculiarity of this experiment is the preparation of palladium nanoparticles, which look like that. Actually, it's a geometry of quasi-crystals. And what I'm going to do first after coming home is to look at what is known about the breather formation in quasi-crystals, because my idea is probably, I think somewhere, no doubt, that they can be linked, because quasi-crystals, it's something in between order and disorder. And if this hypothesis is true, it can bring us real progress to engineering engineering breathers and engineering linear. And the last slide to actually demonstrate your question and to answer it is the rather recent work by Zhang and Douglas. You see, this is an MD simulation of nickel nanoparticle at 1000 K. It's not 0 K, it's 1000 K temperature relevant to ECAP. And you see different colors demonstrating different energies, which means clear localization of energy on quasi-particles. So you're right. Thank you. Professor Chomsky